Okay, so this part is probably the most valuable part of the presentation that I put together. This is all new. One of the things that I have found lacking in many of the training materials, either from the vendor or that have been done, is that there wasn't really a start to finish how to build a model. So I came up with this real world example. This is from one of our mission design labs. I got permission from the principal investigator to sanitize it as much as possible and say, all right, let's see what happens if we start from CAD and all the things that a thermal engineer needs to know, the orbits, the dissipations, the temperature requirements, CAD, stability, gradient requirements, and kind of create you've been tasked to build a model. So, this is making the assumption that you know all the things. It's going to be shown that we have all the information we need to build the model. So this was a design built around an Espa Grande, where they're going to add a propulsion capability to this. There'll be another vehicle on top of here. The bottom of it interfaces with the launch vehicle, and then the top vehicle would separate, and this would then separate and fly away and become its own spacecraft. There are 3 instruments that are supported off of the ports here. So this direction is nadir. You've got an instrument looking down here, an instrument looking down here, an instrument looking down here, some cameras looking down, and it flies in this direction or this direction. We did, in this design, say that there's a yaw flip. So it does go from a beta angle of -90 to +90. So if you come up, hit beta 0, and your radiator's now going to start getting illuminated, well, now turn around and fly backwards, and now your radiator's going the other direction. You can kind of see that here. As the beta angle were to go up here, now the radiator on this side would start to get some sun. So we turn around and fly the other direction, and the radiator is facing in this way. So if you're familiar with TRIM or GPM, they do that. So it's a common technique in low Earth orbit kind of mission. So this was the launch date, the altitude. You can see the beta angle progression, for different days of the mission. So we do go all the way -90 to +90 and do the yaw flip, so we don't get any direct solar. So that keeps one side of the spacecraft nice and cold for us. That's where we'll put our radiator. So sanitizing all of the requirements for the components. We've got A through N, what their temperature limits are, operational and survival. We've got the current best estimates for the power. In certain cases, there are ones that have different modes of operation. And then they're listed here as to what it is. So we'll get into some of the details as to how you would model that. There are different ways to do it. I prefer myself, when I have things that are time varying, to control it in Cinda logic rather than trying to use a time varying heat load in desktop. It gives me more flexibility, but it could be done multiple ways. All right, so this is the CAD layout. Here it is. We've got a 2-axis solar array. It will gimbal around to keep us locked onto the sun. If we remove the solar array, you can kind of zoom in here. If we remove the instruments, you see there's this closeout. Inside here, we've got essentially 3 decks. You've got a deck 1 with the avionics mounted to it, with another one on the coal-facing side. Deck 2, we've got this pyramid structure with some components on it. And deck 3, we've got these other components here. I'm sure you can infer what these are, but I won't tell you. And then these are 3 other components that are orthogonal, so one in the X direction, one in the Y direction, one in the Z direction. So these are all the components that are there. So we're going to go through and describe where A, B, C, D, E, F, G, H, I, J, K, L, M, and N are. If I were to take and hide this component, you can see it's got these holes cut in here. So, there's some flanges at this component that mount it to the deck. There's a component that hides out here on this boom that contains these 2 dishes at either end. So there's one component here. Similarly, there's, one of the others is mounted external to the spacecraft in the vertical direction and one horizontal to the bottom of a plate. All right, so assumptions going into this model. The ESPA, the decks, the brackets, the avionics, pretty much everything is aluminum. The only non-aluminum component is going to be component N, which is titanium. We're going to make the assumption that the boxes are going to reject their heat through baseplate conduction. We're going to neglect radiation off of the sides. So that really means that if we're ignoring radiation from the sides of boxes, we can just model the box baseplate and its conductive interface down to its substrate, rather than having to do the walls to get the radiation there. We're going to assume that the ESPA structure itself is covered with multi-layer insulation. We'll assume a germanium black Kapton outer layer and an E-star effective emissivity of 0.05. We're going to use the plus Y face, deck 1, as the radiator. So if I look here, basically the opposite side of this from where all the boxes, or most of the boxes are mounted, is going to be our radiator. That faces deep space at all times. This truncated pyramid on deck 2 is also aluminum. We're going to use that to conduct the heat for the components that's mounted to it down to the deck. The deck will then conduct it up to the walls. Walls will conduct up to deck 1, and then out the radiator. There will be some internal radiation too, but basically the heat is going, outward to the walls, up to the radiator, and then out to space. Everything else, for the most part, is blanketed, so we've got one door for all the watts to get out. Decks 1, 2, and 3 and the closeout are all going to be bolted around the perimeter with 24 bolts. We'll assume 2 watts per K per bolt to the ESPA structure, so it's well coupled. Component N is going to be thermally isolated from the deck. We're going to assume we need heaters there, so we've got 4 locations there, 0.1 watt, should be 0.1 watt per K each, around the midplane. And in the version that you download, all of the sample files that you need to get started are contained in here. It's got the final one, it's got the CAD, so everything you should need to walk through these steps is contained in there. All right, so when you're starting a model, when you've got, even before you have any CAD in there, you want to clean up some things. So you'd open up a new model, save it as something, create the optical properties that you think you're going to need. Very often you'll import them from a previous mission. Nobody wants to have to always enter a new black paint or a new silver Teflon or new white paint or things. So you go and get the properties that you used from the last one. Always a good idea if you have traceability to your properties to include it in there. It's a good place to put it in the comments is, hey, this came from this source, because inevitably at reviews, somebody will ask you, how do you know your properties are good? Where'd you get your conductivity for aluminum from? Do we know we can trust it? And then, you're probably thinking about, well, what are the variables that I'm going to have? So you want to define some symbols. All of my component dissipations are going to be variables. So I've got Q for component A all the way down through M. And then I had 3 other cases here. I've got a hot case flag, which I can then use to change whether I have hot dissipations, cold dissipations, no dissipations. There's a power scale flag, which I like to use when you have uncertainty. When they've given me the current best estimate, we don't want to assume that they're going to come in at the 30 watts they say. We want to size it for a little bit larger. We typically go with 30%. So if I have a power scale factor, I can, in the heat load, apply Q component A times the power scale. If I make the power scale 1.3, now I've added 30% to all of the dissipations. And then there's a lock array beta 90, which will show that basically you reach a singularity with the 2-axis symbol with the beta 90 that, one rotation is all it needs to get it oriented, so then it could be anywhere around that one rotation, and so it could be angled somewhere kind of funky. So this lets you control the second axis of the 2-axis array system. So here we go. We define the thermo-optical properties, the thermophysical properties, set up what the units are, so on and so forth. So that's getting the model ready before you have any CAD or anything that you need to start building. These are the properties and things that you'll reference from there. So then you'll get the CAD. You need to prepare the CAD. Very often, if I bring in a step file, it's going to be one block. A block in AutoCAD is, everything is contained in this one object. You select the whole thing. So you need to explode or burst that block down to its constituents. So I burst it, it's going to burst it down to the next level of assemblies. So you have to keep bursting and bursting and bursting and bursting until all you have left are non-blocks. Because now you've taken all of the assemblies and turned them into 3D solids. Once you've done that, then you can separate them onto different layers and control the visibility by freezing or thawing the layers. And so I'll have one layer for each of the decks, one for the main avionics, the middle avionics, the bottom avionics, miscellaneous stuff, solar arrays, spacecraft, so on and so forth. So This is a good way. You can explode rather than burst, but I suggest you use the burst command. Explode, if you have a 3D solid, would explode it into its constituent side parts to make it up. Burst will not explode lower than a 3D solid. So, the advantage of 3D solids are if I need to cut through it, they're Boolean operations I can do to slice and dice and figure out what a thickness is on things. So burst is preferable to explode, but you could explode and say, well, don't explode blocks. All right, so in order to change the layers for things, you select it, and then you can right-click and bring up properties, or you can type in properties with it selected, and it'll give you these things. So these are properties specific to AutoCAD. So what layer does it appear on? What color is it? Another handy one is does it have transparency? So if you've got something that you want to kind of be able to see through, you can set the transparency to 85%. So those are the three that you tend to use the most. Alternatively, there's a drop-down box at the top of the toolbar. So if you selected something and then go up to the layer, you can select what layer it goes on. So you could either do the layers here, or you could do the layers there, colors, and so on and so forth. So there are different ways to affect the properties, and so on and so forth. All right, so preparing the CAD, these would be the different layers that we would put everything on. So we'll have the ESPA, which will include the instrument panels. We'll have the solar array. We'll have the instruments themselves. We'll also have the different avionics. So we'll have deck 1, all the avionics on it, the deck 2, the pyramid with its avionics, deck 3 and its avionics, and then the whole model. So this is just basically making it easier for you to turn on, turn off the visibility of the things that you want to be working on at a particular point in time. You don't want to be trying to do the boxes inside here with everything else turned on, because it's going to be hard to see anything or pick anything, because it's going to pick things that are closer to it as far as the point that it finds for selection. All right, once you've got the CAD done, before you do any geometry modeling, probably create the orbits. Those should be known. So you'd come in here, select the beta angles for it. In this case, we went through 0 to 90, steps of 15, because we wanted to basically sweep through and find out for all the different beta angles, are there any ones that are a particular concern or a problem. And so you would create the orbit, and then you can see that all these other symbols get created. There's some of these that we're going to choose to make sure they get output as a symbol to Cinda, or a register to Cinda. By default, that doesn't happen, but we're going to have things that are dependent on time as far as our dissipation goes. So we want to know what the period is for the orbit. We want to know when the eclipse entry and the eclipse exit is, because one of the components turns on when you're in eclipse and turns off when you're out of eclipse. So passing this information into Cinda allows you to utilize that knowledge based on the time n variable in Cinda. I can check that against where I am locally in the orbit to see whether I'm in eclipse or not. So you would select those symbols and then check the box that says, always output as Cinda register. So we define all of these orbits. Here it gives you, the fluxes to use for hot and cold, how many positions to have, and so on and so forth. So as a student, you can go through and do these on your time. All right, so now we'll get back into the actual showing how to do it, and this is going to be some of the geometry building. So I'll sit down again for this, and we're going to try to go half screen and half screen. We'll see how well that works. And Shinichi-san, if you could let me know when we hit the break, I would appreciate that. So, because otherwise I'm just going to cruise right on through it. All right, so we'll go ahead and close this thermal desktop. We don't need it anymore. Never did save it. So file, save as. All right, so file, open, and for simplicity, I'm just going to pick the final one we had, and we'll just build a copy of it. So. All right, so this is all the thermal. So let's go ahead and just turn all this off for now because we don't need to see the final model. So I'm going to turn on the visibility for CAD ESPA. And if it doesn't come up here, then I'll probably, because I've turned off the layer, I would have turned off the visibility for this. So you can turn the visibility back on again, even for things that aren't thermal desktop objects by doing turn visibility on, select all. And so now it's got the ESPA. It also turned on all of my thermal surfaces. So let's just globally turn, we don't want to globally turn thermal surfaces off yet, because we're using them. So we'll again turn off visibility. So here is my CAD ESPA page. So for now, I'm just going to make a copy of this. And I'm going to go from 0, 0, 0 to 0, minus 2,000. I can't remember the units. Let's check. Okay, I'm in inches. Don't want to go 2,000 inches. All right, so we're going to make a copy of this to work with it. We'll move it 200 inches away. Okay, so there it is out of the way. So if I list this entity, you can see that it's a 3D solid. So that lets me do things with it. I could slice it. So I come in here and say slice. And since it's a 3D solid, an object that knows what to do with it, I can say, all right, I want to slice it about the YZ plane. I'm going to pick a point on the YZ plane, which we'll say is the center. Okay, and I'll keep both sides. Okay, now I've sliced it. I can delete this side, and now I've cut. I can look and see what a thickness is here. I could go distance from midpoint to perpendicular, and get a distance there that says, oh, okay, it's ½ an inch. So this lets me do some things to take measurements and build points on here. So we're going to start by creating a thermal desktop cylinder. We're going to go from the center here to the center at the top. And the diameter we're going to take is, let's just go ahead and take it to the outer diameter here. Okay, now it's asking me for starting angle, ending angle. I'll take the defaults for that. And so now it's asking me, okay, you've created a cylinder. What do you want to do with it? So for now, let's just say okay, and let me shrink Thermal Desktop and see if I can put these two side by side. All right, so instructions here tell me to nodalize it as edge nodes, 17 around the circumference by 9 up the height. So we're going to do subdivision, edge nodes, angular is 17. The reason it's 17 is because we want 16 segments. The 17th loops around and merges with the other nodes. So if you do a full 360 and you want a nice even increment, add 1 to it. Otherwise, you'll find that you'll have strange units there. Height doesn't matter. It's just going to be linear at that point, not circumferential. So 13 by 9, and we'll hit OK. And so now here are my surfaces. And let me turn on the nodes. And so one of the things you can do is if you wanted to put a rudimentary hole in an object, you can disable the node. And if you disable the node, then the surface area associated with it and the conductive properties that would be calculated will get ignored. And so we're going to do that here and just show that if I take these 3 nodes and these 3 nodes, and let's see, it's going to be 3 nodes here, 1, 2, 3, and let's just edit those for now. So if I come up here to enable disabled and say it's disabled, make it a 0, you'll notice that I now have a hole in there. So maybe this is good enough if you're doing something quick. I tend to like to use elements a lot. So what we're going to do is basically convert this to finite elements, which is then going to allow me to move some nodes to better represent the shape. And so this is, come on. So this is not sufficient for my needs, might be sufficient for yours, but it's good to know that you can put a hole in something like this. You know, again, it's just going to be, what do I do? The surface area associated with that sub portion of the surface. It's not anything where you can change the size and shape and orientation of it in order to do that. All right. So this next thing I'll show is really a one-way operation. You can convert a finite difference to a finite elements. And what it will do then is this will now become a four-sided element, this will now become a four-sided element, this will become a four-sided element, and you are locked in at that point. I could change this orientation now and say, okay, well, instead of being 17, let me make it 27. But once you've converted it to elements, you don't have that flexibility anymore. Elements are four-sided or three-sided for planar, and then they can be either wedges, bricks, pyramids, or tetrahedrons for solid type elements. But I like to work with elements because they give me the most flexibility. So we're going to come here under FDFEM network or modeling tools, always forget. Okay, there we go. Convert finite difference to finite elements. And so once I do this, it's done. Now I have elements. So you'll notice that it doesn't take care of the fact that, you know, I had some things that were turned off, but I could come in here and say, well, let me just delete these elements manually. And so now you can see that now I can make this hole a little different. I can move this element here, or not this element, this node here, and do it. So in this case, we're going to remove some larger sections of this in order to make the hole. So we're going to get rid of that. And we'll come around and do it on one of the full size sides, because that's where we're going to work. All right, so delete that. All right, so let's see. Adjust it. All right, so okay. Actually, we'll work with the corner one here. All right, so first thing I want to do is I want to mimic this whole shape. So I'm going to take this node right here, and I'm going to move it to this corner. So I've now just adjusted the shape of the element, because when you move a node and there's an element defined by it, again, the shape of the element is based on the node locations, not the element definition itself. Take this one and move it to here. All right. And so I've got some other ones that are going to be place. Okay, I'll call that one probably close enough. But I'm going to want to take this one here and move it. And so this is where you would use the nearest OSNAP object. So I'm going to select from node, and then I'm going to say, I want it to be near this curve somewhere here. And so you can see that as I move along here, it's got this little hourglass symbol. That shows you where it is, but it's going to pick a point on that. So nearest lets me move that node there. And then I'll take this other one and move it from the node location to near to this point. Okay, so now if I turn off the ESPA surface, you can see that I've got some things that moved where they should. I got surface that I deleted that I might need to recreate. I'll have to remember whether that was supposed to be there or not. So I might need to recreate this element. So let's just go ahead and do that. Let's create an element again. So I'll come over here to the element, create node 1, node 2, node 3. And I'll do the same thing for down here. And this follows the right-hand rule. So clicking 1, 2, and 3, follow the right-hand rule means that the element normal will be pointing away from the surface. Wrong number of nodes. Okay, so it needs at least 3. Okay. So there I've made half of it. For symmetry, I could mirror the other half around. So let me mirror 3D. And we're going to mirror this element, about the XY plane, sorry, the YZ plane. And a point on the middle is going to be right here. Delete the source objects, no. And now I've mirrored this element over to here. And I could then say, okay, well, I recognize that this is moving here, so let me move this node to this location. And I'm going to move this node to this location. That's replicating what I have over here. So now I have a rudimentary shape that's kind of the size of the hole. It's not quite perfect, but it's probably good enough for the purposes that we have here. These other nodes in the middle have now been orphaned. I can delete them. And so then I would go through and I could mirror this around to the other sides. So let's just go ahead and say I'm going to take and delete so now what I have is 1/4 of this, 1 quadrant. And it should be 90 degrees. And if we look at the top, sure enough, it looks like it's about 90 degrees. And so I need to mirror it, but I forgot to save myself a point. So let's turn back on the ESPA. Okay, because what I need to do is I need to do an array classic, and it's going to be a polar array, and I'm going to basically rotate this around and make 4 copies of it. So let's do a line so that I have a point to, not list, to use as a marker. So we're going to do a line from the center of here, and we'll just have it go up. That's my axis of rotation. Now, one of the things with the array classic command is it is always about the user coordinate system z-axis. And you'll notice that my z-axis is pointed in this direction. So let me do a UCS, stands for user coordinate system, and I want to rotate about x by -90. That now puts my y or my z-axis facing up. Okay, so now I can turn back off the ESPA because I don't need it. And I'm going to do array classic. And I'm going to select the objects. I'm going to do all of the nodes and all of the elements. I want to do a polar array. My center point, I'm going to select here. It's going to be the end of this line. I want 4 times, and I want to go 360 degrees and fill it in. I can preview it. Lo and behold, there, bang, I've got my ESPA structure. So I can say hit return. And now I've got my 4-sided structure, 4 holes in it, good to go. Now, when I did that, it made a copy of this array around, or this element over here. So I'm going to have some places where I don't have things lined up. One way to check that is under thermal model checks and check free edges or show free edges. And so here, if I do this and then turn off the visibility, you can see all the places where I have edges that didn't have nodes merged. So not a surprise that I have it here, and here, and here, and here. A little bit surprised. I forgot that I needed to merge some nodes over here. That was where I moved the node in, and so it looks like it's merged, but it isn't. So now if I were to bring back up the nodes and then say merge here, select all of these, say, okay, give a tolerance of that, 60 nodes found. Let me delete this free edges and then turn the elements back on, and let's check the free edges again. And then all I should see is this top ring, the bottom ring, and the 4 rings on the side if everything was done properly. So thermal model checks, check elements, not check elements, show free edges. And again, you have to hide the surfaces. That looks good. That's what I want to see. I've got free edges here. That means there's no other element along that edge, no other element along that edge. So I would expect it at this top and these sides. So that is the creation of this ESPA structure. All right, so moving on. We're now going to create these little flanges here for the ports. So let's turn back on the structure so that I have points to do something with. All right. And so in this case, I'm going to create a disk that's going to have its center based on the center of this, and I'm going to give it a certain number of points around the edge. That's going to give me pick points to be able to have nodes that I can then make connections with the elements back to the nodes at the structure here. So I've got basically 1 point, 2 points, 3 points, 4 points, 5 points through a half piece. So that's going to dictate how many nodes I want to have around there. So we're going to create a disk about the center there, and the z-axis is going to be coming out, and the size of that disk is going to be based on this distance, except the full 360. And I'm going to want edge nodes. I want radial to be at least 2. That puts 1 at the center and 1 at the edges. And then around the outside, I needed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is that right? Let's see if 13 was it. Oops. Radial is 2, and angular is 13. All right, so I think that's wrong. I think that's got to actually be 11. 1, 2, 3, 4, 5. All right, make it 9. Okay. So here we'll line up this to this, this to this, this to this, this to this, and then the bottom. So now I would create elements. So I'll create an element going 1, 2, 3, 4. Create another element going 1, 2, 3, 4. Create another element going 1, 2, 3, 4, and then the last element down here. Let's see, going 1, 2, 3, and 4. All right, so now I can delete this, because I've now made this side, and I can then again use the properties of symmetry to mirror that over. So let's do that. So we'll turn off the ESPA CAD, and then I'll mirror 3D these elements, 1, 2, 3, 4. We're going to mirror about the YZ plane again. And I can select the center point because I know that's good. And don't delete. And now I should have completed this side over here. Now, you guys should be able to guess they're going to be free edges. You know, there's a free edge there. There's a free edge there because this side was mirrored around. So I'll want to merge those nodes, but let's go ahead and copy and do the array classic again with these surfaces around the edges. So we'll do array classic. Again, select my objects. 1, 2, 3, 4. I'm going to want to pick the center point somewhere along this z-axis, 4 points or 4 items to fill, preview it. They're my ports. So I can hit return to accept that, merge the nodes. And now again, check my free edges. And again, I should still have this port free, and then the top and bottom. So again, it should look like the same 6 circles that we saw earlier. Checks. Okay, so something's not right there. We've got to see why that is, because that shouldn't be there. So let's go and investigate. Maybe that is right. I have to figure out. I'll admit I'm slightly stumped as to why that's thinking it's a free edge. Wait a minute, I know why. Because there are 2 of those there. So there's one here, and then there's one here. So this was the old free edges, and this is the new free edges. So one of the things, if you're using this, make sure you delete the polyline that represents the old free edges. So let's go ahead and just check and verify that indeed that is correct. So we'll come back here. We've deleted all the free edge lines that it showed. Model checks, show free edges. Now I'll turn off the surfaces, and there's the correct number of free edges that we have. All right, so moving on to the next slide. So we kind of already did this. Moved some things, created this, and then went through here, mirrored it, showed the free edges. So I think that is there. So, all right, so we've created the geometry we want now for the main ESPA structure. Let's just go and delete that off. Okay. But now we need to turn this into actual modeling artifacts, you know, to give the rest of the properties. So let's check that we have the correct top side for everything. Okay, and that's what I want. I want all the blue to be on the inside. I want all the green to be on the outside. It's entirely possible that maybe I had made one of these elements wrong, and it would be the other direction. So let me show you. So this is what they call reverse connectivity. So it lets you flip the direction that the element is. So here you can see that maybe I made one of these wrong. The green is facing in, blue is facing out. So if it's just one of them, it's not too bad. You can manually do that. If I had a whole bunch of them, then I would probably want to go through and do the modeling tools, and then there's a model checks. Synchronized element normals here under FDFEM network. And so I could say, this is the one that I want to be the guide, and then all the other ones I want to follow that same pattern. And so there, because this one was pointing out, all the rest of them are automatically shifted such that their element normals are pointing in the same direction as that. So definitely want to check that, because when you start assigning optical properties to the top and the bottom, when something's being top and something's being bottom, then it becomes a bookkeeping nightmare to make sure that you assign the correct things to the correct surfaces. All right, we have a bunch of nodes here. We've merged them properly, but we haven't numbered them yet. So I can see this will probably be in main, because that's the default. I've got main 1, and of course main 1 is going to occur 20 times. So what I'm going to want to do, and we'll keep this here, is to renumber the nodes. And I need to turn on nodes to be able to do that. Okay, so we'll renumber. I'm going to start that with 1001, incrementing by 1. You'll notice in this dialog box that if you already had some things that were in a different submodel, you can pick the submodel that you want to resequence the nodes. So that will let you, resequence some of them, but not all of them. They'd only be the ones that meet this submodel criteria. All right, we're going to want to assign radiation and properties to this. So we're going to edit all these surfaces. Good news is we're going to say that the radiation is going to be both sides. The top side we're going to do as blanket exterior. It's facing away. The inside we're going to do as black anodize. We're going to set the concap, and we want it to be, so let's call this new ESPA so that I don't confuse it with the old ESPA. I want the property to be spacecraft aluminum. I'm going to select this as an expression to be 0.5 inches. Again, you can see that it's bold. That means that there's an expression entered here. Insulation, I'm going to put insulation on the top side. I need to then select what property I'm going to use for that. In this case, I had one that's got an effective emissivity of 0.05. For my MLI, I'd like to put in a specific heat of 0, a conductance of 0, but a density that is commensurate with a area type multiplier for mass of MLI. I usually use about 0.6 kilograms per meter squared. And if I use that, then I would put in a thickness of 1 meter here, so that now if I do a mass check, I'll get 0.1 or 1 meter squared times the area times the density. That would then give me the mass of MLI. So I'm having to do a quick study and somebody wants to know, well, how much mass do you have in MLI? I can use the model to get that out of there. This thickness does nothing for the computations if it is just an E star. But if I had a conductive thickness, so I had some foam here, then that thickness would be a player. The only other place where this can be tricky is if you have measures. It might try to use the thickness associated with that and then put the measure inside the thickness or inside the volume that's taken up between the outside of the insulation and the underlying structure. But if it's just an E star, you don't have to worry with it. The other thing that I do as a matter of course is I always set my offsets to 100,000 or 200,000 if it's on the other side, for both of them. And then I always keep all my other nodes below 100,000. That means that when I look at CINDA output, if I see 100,000, I know it's MLI. I probably don't have to care much about the temperature. Lets me help filter out things when I'm looking at it in Excel to say, this node doesn't really matter much, it's MLI. These nodes do because they're not MLI. So those are some modeling practices that I tend to follow. let's see. Okay. All right. Now, one of the things you'll notice, if I edit an element, you'll notice that there's some of the tabs that aren't there. When I was doing the cylinder, I had properties for its radius and its starting angle, its ending angle. I had subdivision. I had node numbering. With elements, you don't have that because you have to define the element by the nodes that make it up. So you can't go and change the node numbers for an element. You can't change the size of the element other than by adjusting the nodes. So you're limited in the tabs that you see here compared to a surface. So just something to note. All right, so now we want to do some more model checks. Did I put MLI on the right side? So let's check and see insulation nodes, and looks the same. Let's say that I forgot to put insulation on this node, or I unchecked it, and then do the display again. Okay, now it's showing me that, hey, this one doesn't have it. It's supposed to. I like the old way that they did it better, where they colored it red instead, and I think there's a feature to get back to that, but I'm not sure what it is off the top of my head. I think it's set that way on my old computer, but not on this new one. So it tells me here that there's something that is not being displayed properly. So, so let's turn on main again. So I want to reset that and then apply the insulation back to this again. I want to check that I have active properties, so let's go ahead and make one of these not be active on both sides, just so we can show that it's different. And so I can display by active sides for the current analysis group, and I could select what that is here. Analysis groups are basically different radiation configurations that you could have. So you could have one side in an internal group, other side in an external group. You could have a group for all the GSE and a test configuration. You could have some for, I've had separation for the launch vehicle. So radiation analysis groups are a nice way of working with the configuration of a model radiatively, where you can have different active sides and such defined for that. In this case, we just have one in its base. So we'll go ahead and display. Actually, there it is. Draw items with no data and wireframe. We don't want that. All right, so display. So there you can see yellow means that both sides are active. If it were not in the analysis group, it'll be red. And if it's dark blue, that means that it's active none. So I'll show you what that looks like. So if we head here, so these are the 5 options. Top out, side that I'm looking at is active. Bottom in, side that's opposite what I'm looking at is active. Both sides, none, and not an analysis group. Now these two are different. Not an analysis group, it's not there at all. Doesn't see it. If a ray hits it, it goes right through it. None means that it participates in radiation, but the energy that's associated with the ray trace is not tallied or included in the solution. So you might have none as a blocker surface, because all the sun's rays, I want to block coming in, and I might want to look at how much energy that was coming in through an aperture. I might have a base plate where the substrate is radiating up, but I know that it's smushed down there, so let me make the active side none so that it absorbs it but doesn't tally it up or keep it in any way. So none and not an analysis group are two very different things, so be careful if you're using none to really understand what its behavior is. All right, so we'll do that none. And so there you can see this is dark blue, which indicates it's active none. All right, so let's set that back to what it's supposed to be, which is both sides active. Okay, did I cover everything here that I wanted to? Did I do the material property?
Take a break.
A break would be good. So.